Hello everybody. Myself JV Apparo, Assistant Professor in the Department of EEE, CSE Institute of Technology and Engineering. Today I would like to discuss about microprocessors and microcontrollers. Coming to the first one, microprocessor. Basically, microprocessor and microcontroller, these two are the two distinct words. First we would like to discuss about the microprocessor and then we go for the microcontroller. Coming to the microprocessor, simply it is a programmable device that takes the inputs and performs some mathematical and logical operations on that particular input and gives the result. This is about the main purpose of this microprocessor. Simply it can accept or it can take the input signals from the memory or from the IO devices, and then it can perform some arithmetical and logical operations depending on as per our requirement, and finally it can give the or produces the desired output. This is about the microprocessor. In simple words, a microprocessor is a digital device. That means simple, it is an IC. This is an integrated circuit, which can fetch the instructions from the memory, decode the instructions, and finally execute them and give them the results. Here we are discussing about total three terms. The first one is the fetching, and the second one is decoding, and third one is the execution. Total three steps are there. The first one is the fetching, and second one is the decoding, and third one is the execution. These three are the defines the complete operation of a microprocessor. The first one is the fetching the instruction. That means simply it can fetch the instructions or it can fetch the data. Fetching means gathering or collecting the information from the memory device or IO devices. After fetching the instructions, it can decode the instruction. That means simply it can convert the instruction which are understood by the processor unit. And third one is the execution. Execution means simply it runs the instruction, it programs the instruction completely. Here, before discussing about these three steps, first we should know about one thing, that a microprocessor doesn't have any inbuilt memory. That means it doesn't have any inbuilt memory or any IO devices. In order to store any data or any information, simply we require some external memory. That means we need to interface the external memory or external IO devices. Here IO device means input and output devices. We need to interface externally these two terms. First one is the memory and second one is the input output devices. These are completely externally connected to the microprocessor. The data which is the required data or which is under the code or program which we can write for this microprocessor is completely stored in the external memory only. Similarly, we can produce or we can give the inputs to this particular microprocessor through external IO devices. Like this, simply the data and the complete program should be stored in the external memory, and we need to access the memory. The accessing or the gathering of instructions from that particular memory is called as fetching. Fetching is the gathering information from the memory device or IO devices. After fetching, it can decode the instruction. One thing we need to tell here, that the data which is given to the microprocessor, simply it is in hexadecimal format. It is in hexadecimal format. After giving this data or instruction, the microprocessor can understand only binary language. The microprocessor can only understand binary language. The decoder unit which converts this hexadecimal data into corresponding binary form, and similarly it can deviate or differentiates the opcodes and operates in that particular instruction. For example, if we take an instruction here, move AX, 05H. This is a simple instruction. Here move means simply move the instruction. Here AX is the register, and 05 is the data. This 05 data is already stored in the memory unit. This is in hexadecimal format. H indicates the hexadecimal. We need to move this particular data into this register. Here our aim is to move this 05 the data into this register AX. So for that we are using this instruction move. So move 05 into the register AX. So this is a simple instruction. So in this instruction we have two different terms here. The first one is the move. So this is called as opcode. This is called as opcode. So opcode is nothing but operational code. So that means which type of operation we are performing here. So that is completely defined by this particular opcode. Opcode is nothing but operational code. Here we are performing a moving operation. So move is the opcode. And then the second one is the data. So we are performing this particular operation on these data. AX is the register and 05 is the data. So these two are called as operands. So this is operand 1. So operand. So this is operand 1. Similarly 05 is the operand 2. So these are the operands and this is the opcode. So the purpose of decoder is to define or to differentiate this opcode and operands. So this is the purpose of decoder. So and after decoding the instruction, the third one is the execution. So simply the processor can run this program and finally it gives the result as per our requirement. So this is about the working of this microprocessor. So the figure shows a simple microprocessor ID. This is 8086. So manufactured by Intel company. So this is completely a 40 pin IC. So here we are having total 40 pins. So each pin having their own purpose or their own specific task. So this is an example for the Intel company 8086 microprocessor. And coming to the evolution of microprocessor. So this microprocessor first mainly developed by the Intel company in the year 1971. So in the year 1971, the Intel first manufactured an IC, that is microprocessor ICs, and it is numbered as 4004. This is the IC number 4004, and this is a 4-bit IC. Here 4-bit means simply this IC can process 4 bits of information or 4 bits of data in one machine cycle. That means one cycle of operation. So simply it can process only 4 bits of data. So this is the 4-bit IC. It was invented by Intel company in 1971. And after that in 1976 the second processor, that is 8085, is developed by Intel company. So this is a 8-bit microprocessor. So means this processor can process 8 bits of data or 8 bits of information. So in between we have one more IC is there, that is 8008. 8008. So this is also an 8-bit IC. So this is also perform 8-bit operations. And after that in 1978 the Intel designed an IC, that is 8086 microprocessor. So this is completely a 16-bit processor. That means this is a 16-bit IC. It can perform 16-bit operations. So by using this IC, we can perform any 8-bit operations as well as 16-bit operations also. That means this IC can be compatible with the 8085 also. So this is the evolution of microprocessors. And we have 64-bit ICs also, but in our syllabus we have only 8086. That means 16-bit processors only. So this is about the evolution of microprocessor. So coming to the block diagram of microprocessor, here we have a main unit, that is microprocessor unit. So in this microprocessor we have total 3 different units. The first one is the ALU, arithmetic logic unit, and second one is the control unit, and third one is the register array. So these 3 are the inside the chip. These 3 are the completely internal components. And here in addition to this internal chip we have connected external device, that is IO devices. So IO device means input device and output device. So these two are the output device and input device. These are the IO devices. These are connected externally to the microprocessor, and this is the memory unit. So we need to connect memory externally to the processor. I already told that the microprocessor doesn't have any inbuilt memory. So we need to connect the memory externally to the processor unit. So this is the complete block diagram of microprocessor. And this is the complete internal architecture of 8086 microprocessor. So this is a shortcut form for the microprocessor, that is mu p. So micro is indicated by mu, so p means processor. So this is the shortcut word for the microprocessor. And this figure shows the completely the internal architecture of 8086 microprocessor. So when we observe this figure, here we are having total 2 units. The first one is the bus interfacing unit. So this is the bus interfacing unit, and second one is the execution unit. The first one is bus interfacing unit and second one is the execution unit. So coming to the first unit, bus interfacing unit, that means this unit is very helpful for the interfacing of the signals with the external environment. That means with the external memory or external IO devices. So I already told that the complete information or complete data should be stored in the external memory only. So we need to fetch the information from the memory or from the IO devices. So for that purpose we are using this particular unit, that is bus interfacing unit. That means changing or transfer of information from the external devices, that means memory or IO device to the processor unit. Here the information can be to and fro, that means from the memory to the processor or from the processor to the memory. So this is about the purpose of bus interfacing unit. And the second unit is the execution unit. So after fetching the data completely, the decoder unit will completely decode the data, and after completion of this decoding circuit, so the execution will be performed by this particular execution unit. So this is the execution unit. And coming to the individual components, so here we have some general purpose registers, AX, BX, CX and DX. So these 4 are called as general purpose registers. So here these registers will be used for store the general, that means data. So this indicates the address of the general data. Here the AX is called as accumulator. The AX is called as accumulator. So the purpose of accumulator is to store the temporary values or temporary results. That means if we are performing any operation, in between we are generating some intermediate results. So those intermediate results will be stored in this particular accumulator. So this is the purpose of accumulator, for storing the temporary values or temporary data or simply auxiliary results. And these 4 registers are completely 16-bit registers. These 4 registers are completely 16-bit registers. That means they can store 16 bits of information. Here these registers can be divided into 2 parts. For example, if we take the AX is divided into 2 parts. One is the AH and second one is the AL. That means higher byte and lower byte. AH is the higher byte of A and AL is the lower byte of A. That means this is the 8-bit register. AH is the 8-bit registers and AL is also an 8-bit register. So we can use individually also. That means if we are performing any 8-bit operation, then we can use either AL or either AH. Suppose in case if we are performing any 16-bit operation, then we can use the complete AX register. This is for 16-bit operation. So like this we have total 4 different registers, AX, BX, CX and DS. These are for storing the data, AX, BX, CX and DX. And coming to the next one, these are the segment registers. These are the segment registers. Here we are having total 4 segment registers. So CS means a code segment, SS means stack segment, DS means data segment, ES means extra segment. Total we are having total 4 segment registers: code segment, stack segment, data segment and finally extra segment. So these 4 segments or segment registers will indicate the segment address. That means the starting address of that particular segment. For example, the data stored in CS will indicate the segment address of the code segment. Similarly, the data stored in DS, data segment, will indicate the segment address in the data segment. So we will discuss about these segments in the coming slides. And next one is the pointer registers and index registers. Stack pointer, base pointer, and again instruction pointer. So these three are called as pointers: stack pointer, base pointer, and instruction pointer. And these two are the index registers: source index and destination index. So these registers are called as special purpose registers or special function registers. So these are completely used to store the offset data. These are used to store the offset data or offset address. So these registers can be used for offset address, and these registers can be used for segment address. Segment registers will store the segment address, and pointers and index registers will store the offset address. So by using these two addresses, segment address and offset address, we should calculate the physical address. Here PA indicates the physical address. PA nothing but physical address. So physical address is nothing but segment address into 10. That means the data stored in the segment register should be multiplied by 10, and after that for this value we should add the offset address, so that we can get the physical address of the any memory location. That means simply any instruction, any coming instruction which are stored in the memory, so the address will be calculated by using this formula. Physical address is equal to segment address into 10 plus offset address. So by using this formula we can calculate the physical address of the coming instruction. So this calculation should be completely performed by this particular device, which is used by Sigma. So this is completely physical calculation. And here, so this is ALU. The main part of this particular process is ALU, arithmetical and logical unit. So which can perform any operation, which can perform any arithmetical operation, any logical operation. So this is the main processing unit. So the data which is fetched from these devices, from after calculation of this physical address, simply we can fetching the instruction from the external memory, and after that the data will be processed by this particular ALU. This is the arithmetical logical unit. And this one is the flags. So this is also a 16-bit register. Flag is also a 16-bit register. It shows the status of the operation. That means after the completion of any operation, that means any addition, any multiplication. So after the completion of any operation, the results will be updated here. So this is the flag register. For example, if we are performing any addition or any subtraction, so after completion of addition, if we are having any auxiliary carry or any carry, so that auxiliary carry flag will be set here. Similarly, if any carry is generated, the carry flag will be set here. So like this, if any parity is obtained or any sign flag, that means the result is positive or negative in case of any signed operations, so the results will be updated here. This is the flag register. That means the flag register will show the complete status of the result after the completion of the execution. So this is about the flag register. And this is the 6-byte free fetch queue means. So completely, as in previous, we have in total 3 operations. The first one is the fetching, and second one is the decoding, and third one is the executing or execution. So if the first instruction is fetched, then it go for the decoding stage, and after that it go to the execution stage, that is third stage. So whenever the first instruction is in the execution stage, then the processor will start the second fetching. That means the second instruction will be fetched here. So after fetching and decoding of second instruction, the second instruction will be stored here. So after that, the third instruction will be fetched and decoding and will be stored here. After that, the fourth instruction will be stored here. So like this, simply the processor can fetch the instruction and decode the instruction, and the instruction is ready to execute and it is available in the queue. So this is the queue unit. That means it can store the complete 6 bytes of information. So if the first unit is already executed and our execution is completed, then the second instruction from the queue will be go to the execution unit. Then the ALU will start the executing the second instruction. So like this, the instruction will be wait in this queue. So this is the queue, 6-byte queue. So this is about the complete architecture of 8086 microprocessor. And coming to the segment registers, here we are having total 4 segment registers. The first one is the code segment register, and second one is the data segment register, and third one is the stack segment register, and fourth one is the extra segment register. So these 4 segment registers, that means code segment, data segment, stack segment, and then extra segment. So these are all 16-bit registers. These 4 registers are the complete 16-bit registers. So these registers will store the segment address. That means the starting address of this particular segment. So code segment will store the starting address for the code segment. Data segment register will store the starting address of data segment. Similarly, stack segment register will store the starting address of the stack segment. So like this, complete these all registers will store the starting address or segment address of this particular segment. So to know about these segments, first we should discuss about this memory. So the microprocessor can access 1 MB of data, that is 1 megabyte. So this is the physical memory unit, for example. So here the physical memory is divided into number of logical segments like this. Like this, we are having total 16 segments. We are having total 16 logical segments. So 1 MB means, so this is 1024 bits, 1024 KB. That means if we divide this 1024 into 16 slots or 16 segments, we are getting 64 KB. That means the size of each segment is 64 KB here. So this is the memory segmentation. That means the physical memory is completely divided into 16 logical segments, and each segment having a size of 64 KB. So here in these segments we are storing data, codes, stack, or any extra data like this. So means we are storing the data or code or stack or any extra data in these segments. So if we segment these memory like this, so it is completely better to fetch the instruction in an easy way. For example, if we consider an example, suppose if we have any area, so in this area we have total 100 houses, so like this. So total 100 houses are there, and these houses are numbered as 1, 2, 3, so on up to 100. So these are completely randomly located in that particular area. So for example, if you want to know the 67 house, this is our destination place. So to find this 67 house, one should first need to go to the first house, and after that he should go to the second house, and after that he should go to the third house. Like this, he can go to the 67th house. That means completely he can attempt up to 67 times for reaching the destination place. So this is completely a time taking process. So here we are considering second method, that is we are locating these houses in 10 by 10 format. That means 10 rows and 10 columns format. So this is row 1, row 2, row 3, 4, 5 up to 10 rows. Similarly 10 columns. So like this 1, 2, 3, 4, 5. So if we are locating these houses, these 100 houses into 10 by 10 format, that means 10 rows and 10 columns. So if we want the 67th house, so we can directly go to the 6th row. So this is the 6th row, for example. So in first attempt we directly go to the 6th row, and after that in 6th row we directly go to the 7th column. So this is the 7th column. So this is the required destination. That means here we are having total 2 attempts. In first attempt we should directly go to the 6th row, and the second attempt we should directly go to the 7th column. So like within 2 attempts we should reach our destination. So this is the second method. So when we comparing these two methods, the second method is very simple and it is completely a less time taking. So that's why this is a time efficient method. So the same second method will be applicable for this memory segmentation. So if we divide this memory into this like segments, simply we can go to the starting address of any segment. For example, I already told that the code segment register will store the code segment address. For example, this is the code segment. So this is the memory, and in this rack we are having code segment. So this is our required destination. This is the required destination. So here, to reach this destination, we are having total, we require two addresses. The first one is the segment address, and second one is the offset address. Segment address and offset address. The segment address is nothing but the starting address of this particular segment. So this is the segment address. The segment address is nothing but the starting address of the code segment. Here, the code segment register will give the segment address. The code segment register will give the segment address. So this is given by CS, code segment register. And then this IP, that means offset address, will be given by the instruction pointer. The offset address will be given by the instruction pointer. So this is the offset value, this value. So the first one is the segment address, which is given by the segment register, and second one is the offset address, which is given by the instruction pointer. So by using these two addresses, we can simply calculate the physical address or real address of the data. So this is the calculation. So from this, we are having complete two addresses. The first one is the segment address and second one is the offset address. The segment address will be given by the segment register, and offset address will be given by the instruction pointer or any other register, that means stack pointer or base pointers. So by using these two addresses, we can calculate the physical address or real time address of the any instruction or data within the memory. So this is the instruction pointer, which gives the complete offset address. This is also 16-bit register. This is also a 16-bit register. So it gives the offset address. For example, the code segment register having an address of 4321H. This is the address stored in the code segment register, and this is the address stored in the IP, instruction pointer, that is 1000H. So by using these two addresses, that means segment address and offset address, we can calculate the real value, that means physical address. So that further the formula is the code segment address. Our segment address is multiplied by segment address will be multiplied by 10. That means 43210. Then the offset address will be added to this number. Add the offset address. So 01244. So 44210H. So this is the physical address of the instruction or required data. So to calculate the physical address, we require total two addresses, segment address and offset address. So this is about the memory segmentation. So already we discussed about this one. The entire memory is completely divided into 16 logical segments. The entire memory is completely divided into 16 logical segments. So here using one segment for data. So this is for storing data, and this segment is used for store the code, and this is for stack, and this is for extra data. So like this, we are completely divided the entire memory into different segments or different racks. So that we can easily access that particular data in this segment. So for example, if we require any data at this location, so for that we require simply two addresses. The first one is the data segment address. So the data segment register will give the segment address. Here segment address means the starting address of the segment, that means here. So this is the starting address, here. So this is the starting address of the segment. The starting address will be given by this particular data segment register, and after that we require offset address. So this will be given by the any offset register, that is any pointer registers. So with the help of this particular offset address, simply we can calculate the physical address like this. So we can add the segment address to the offset address, simply we can calculate the physical address. The segment address is multiplied by 10 and then add the offset address, so that you can get the physical address of this particular location. So like this, simply the entire memory is divided into 16 logical segments. So this is about the memory segmentation. So this is the formula for physical address calculation. So physical address is nothing but segment address into 10 plus offset address. For example, if we take the segment address as 1, 2, 3, 4, this is the segment address, and the offset address is 1000. So this is the segment address and this is the offset address. So to calculate the physical address, simply we should multiply the segment address into 10. Means it becomes 1, 2, 3, 4, 0. So this is the segment address and the offset address is 1000. So add this offset to the segment address. So 0, 4, 3, 3, 1. So this is the physical address calculation. So like this we can get the physical address of any particular data or information. And coming to the microcontroller, so a microcontroller is a compact IC, so which is designed for specific operation. So basically microprocessors are completely general purpose. They are used for generally for any application. But coming to the microcontroller, so simply these are designed only for specific task or specific purpose only. So these are completely designed for specific application. For example, if you take any example for the microprocessor, for example a personal computer, if you take any personal computer, so this is the general example for the microprocessor. So here if you observe the PC or personal computer, so the processing unit of CPU completely having only microprocessor, but the data required for this one is stored in the external memory. It is completely stored in the external memory. Simply by using any IO device we can transfer the data also. So memory and IO device can be externally connected to the microprocessor. So this is the example for microprocessor. And coming to the microcontroller, so here we are having different applications of microcontrollers like any electrical ovens or any air conditioners. So these are completely specific task purpose, only that are designed only for that particular specific task only. So this is the complete block diagram of this microcontroller. So here we are having a microprocessor plus any other device like a memory unit, IO ports, any other peripherals like timers or counters, converters. So these are completely connected in a single chip. So this is called as a microcontroller. That means a microprocessor plus any other integrated circuits like memory, IO devices, timers, counters, converters, like this. So all are integrated in a single chip. So this is called as a microprocessor. So this is called as a microcontroller. So a typical microcontroller includes a processor, memory, IO devices and other peripherals like timers and counters. So all should be integrated in a single chip. So this is about the microcontroller. So this is about the microprocessors and microcontrollers. And this is for your assignment. So here total we are having total 3 questions. The first one is the explain about the architecture of 8086 microprocessor, complete architecture. And second one is the differentiate between the microprocessor and microcontroller. And third one is similarly same as in the microprocessor, we are having total different types of microcontrollers based on the bit capacity, that is 8-bit, 16-bit or 32-bit. So you can compare these microcontrollers, that means 8-bit and 16-bit and 32-bit microcontrollers. So these are the assignment questions. Thank you.